In this video, we're going to learn how to do the repeated nearest neighbor algorithm. So take 3 deep breaths and let's make this math easy. All right, so in one of the previous videos, we talked about how you can use the nearest neighbor algorithm to approximately find a cheap Hamiltonian circuit in a graph. It doesn't always give you the cheapest one. The only way you can do that is with the brute force method, but it will give you an approximately cheap Hamiltonian circuit. And in the nearest neighbor algorithm, you get different results depending on which vertex you start with. So the repeated nearest neighbor algorithm is a better approximation because you basically complete the nearest neighbor algorithm for every single vertex in the graph. Like you start at each different vertex and then you choose the cheapest one that you get as a result. So basically the process for this is you just start with one of your vertices. So let's say I start with Seattle, like we did in the nearest neighbor algorithm. And I'm going to complete the nearest neighbor algorithm for that starting point. So I look at all of the edges that go away from Seattle, and it looks like the cheapest one is $70. So I'm going to go from Seattle to LA, and then from LA, it looks like the cheapest one would be 100. So I go to Chicago. And then from Chicago, also remember you don't want to go back to a vertex you've already visited because Hamiltonian circuits only visit each vertex once. So between Dallas and Atlanta, it looks like the cheapest one is 75 to Atlanta. And then I would go to Dallas, which is 85. And then I have to go back to Seattle to close up my circuit. And so that would be the circuit that would be created if I start at Seattle. So let's do the repeated nearest neighbor algorithm with this one. So I have 4 different vertices and I'm going to go through the repeated nearest neighbor algorithm with each vertex as my starting point. So let's start with vertex A for my first one. And if I look at all of the edges that go away from A, it looks like this one is the cheapest one. And so I'll go from A to D, and then from D, I can either go to B or to C, and it looks like C is the cheapest one. So I'll go from A to D to C, and then I have to go to B because Hamiltonian circuits visit each vertex exactly once, and then I have to go back to A to close up my circuit. So I would go A, D, C, B, and then A. And it looks like the cost of that would be 1 plus 8, which is 9, plus 13, which would be 22, plus 4, which would be 26. So that would be the cost of that Hamiltonian circuit. And then I'm going to do the same thing, but starting at a different vertex. So let's say I start at vertex B. Well, the nearest neighbor is vertex A. So I would have B to A. And then the next nearest neighbor is D. And then I have to go to C, which is 8, a cost of 8. And then I have to go to B, which closes up my circuit. So that's also going to cost 26. And then we can do another vertex. And so then the next thing I'll do is I'll start at vertex C. And I'll say, okay, if I start at vertex C, my nearest neighbor is A. Then my nearest neighbor is D. And then I have to go to B. And then I close up my circuit by going to C. So the cost of that one is going to be 9 plus 1, which is 10, plus 2, which is 12, plus 13 is going to be 25. So let me write this out. So I've got C to A to D to B and then back to C. That's going to cost 25. And so that one's cheaper than the other two. You can see that starting at different vertices changes the cost of your circuit. Sometimes, but not always, because starting at A and B ended up giving us the same circuit. But I just have one last vertex to check. So I'm going to start at vertex D. I'm going to go to vertex A, and then vertex C, because that's the nearest one. And then I have to go to B, and then close up my circuit by going to D. So I go to B and then back to D. And that's the same circuit that we found when we started with C. And so that's also going to be 25. So the repeated nearest neighbor algorithm gave us a cheaper way than just starting at vertex A and doing the regular nearest neighbor algorithm. But it still actually doesn't give us the very cheapest circuit, because the absolute cheapest circuit in this graph that we could find with the brute force algorithm is A to D to C to A. So even if you do the repeated nearest neighbor algorithm, it still doesn't necessarily always give you the cheapest one. But again, it does give you an approximation, and it's a better approximation than just doing the nearest neighbor algorithm on a single vertex. So why don't you guys practice and do the repeated nearest neighbor algorithm on this one, and then restart the video to see how I solved it. All right, so on this one, if I start at vertex A, the nearest neighbor is vertex B, because that's the cheapest edge that leaves A. And then it looks like after B, I would go to E, and then to C, and D, and then back up to A. So I'd have A, B, E, C, D, A. And that would cost 4 plus 6 is 10, plus 11 is 21, plus 7 is 28, plus 9 would be 37. So that would be the cost of starting at A. And then if I start at B, I would go to A and then to E. So we'll go B to A to E. And then I don't want to go along the $6 edge, because that would take me back to a vertex that I've already visited, and I haven't, I'm not ready to close up the cycle yet. And then between C and D, which are the unvisited vertices that I still need to visit, it looks like C is going to be the cheapest one. And then I have to go to D to visit all of the vertices, and then I'll go back to B to close my circuit. So the cost of that is going to be 4 plus 5, which is 9, plus 11, which is 20, plus 7, which is 27, and then plus 14, which would be 41. And so that would be the Hamiltonian circuit that would be created if you do the nearest neighbor starting at B. And so then we'll repeat this again, because again, the repeated nearest neighbor algorithm is just doing the nearest neighbor algorithm for all of the vertices as a starting point. So we'll start at C, and it looks like the cheapest neighbor is to go to D. And then from D, it looks like we would go up to A, and then go to B, and then we have to go to E and end up at C. So the cost of that would be 7 plus 9, which is 16, plus 4, which is 20, plus 6, which is 26, plus 11, which would be 37. So it looks like that one costs the same as the blue one. And then I'll repeat this again for vertex D. So if I start at vertex D, the nearest neighbor is vertex C. From there, the nearest neighbor is vertex A, and then vertex B, vertex E, and then I have to go back to D because that was my starting point. So it looks like it's going to be D, C, A, B, E, D. And that cost, if I go 7 plus 8, that's 15, plus 4 is 19, plus 6 is 25, plus 13 is 38, I think, if I added that up right. So that would be that circuit. And then I would do the very last one and start at E. And I'd say, okay, well, starting at E, the nearest neighbor is A, then B, and then C, and then D, and then E. So E, A, B, C, D, E. And the cost of that would be 5 plus 4 is 9, plus 10 is 19, plus 7 is 26, plus 13 is 39. And so based on the repeated nearest neighbor algorithm, it looks like the cost of the shortest circuit is going to be 37. Well, it's not necessarily the shortest circuit, but it's an approximately shortest circuit. And really you could start at A or C, and those two are actually the same circuit. So that would be your approximate shortest Hamiltonian circuit with the repeated nearest neighbor algorithm. So again, these do not necessarily give you the cheapest circuit. They just give you an approximation of the cheapest circuit. But the repeated nearest neighbor algorithm is going to give you a better approximation than if you just do it once. Because if you do it for every vertex, like you can choose the cheapest out of all of them. But if you only do it once, you don't know if you chose the vertex that would actually give you the cheapest. So if you have any questions, let me know, and I hope you guys have a good day.